Hello guys, this is Nick from NVIDIA. Today, I'm glad to share some experience about GPU accelerated training based on MONAI components. As you know, NVIDIA GPUs have been widely applied in many deep learning training or evaluation tasks. And the CUDA parallel computation shows obvious acceleration. And we can achieve better performance with automatic mixed precision and also leverage more GPU resources with the distributed data parallel. But without a clear analysis on the dataset and the training task, it's not easy to fully leverage the GPU resources. Now let me introduce the common approaches with some real-world examples and the demo. First, NVIDIA researchers developed the mixed precision training method, which automatically combines FP32 and FP16 format data during training. The data size is much smaller and the computation is faster. From PyTorch 1.6, developers from Facebook and NVIDIA moved the AMP feature into PyTorch package. It's very easy to enable AMP in a PyTorch program. At the right side of this slide, we can see the speed up when training some popular networks with AMP. I think usually it can be 2 times faster than FP32. I think this is the test on V100 GPU. And if you use MONAI components in a regular PyTorch program, you just need to add the autocast logic as a content provider and create a grad scaler for the backward computation. All the MONAI components can work well with the AMP feature. And just like what we show here in the left side. And if you use MONAI workflows, it can be easier. Just set the AMP flag when you define the supervised trainer or supervised evaluator. The example code is at the right side. So here is some test results of the AMP disabled and enabled on V100 GPU and A100 GPU. We can obviously accelerate the training when AMP is enabled. And with AMP, it even took less epochs to achieve the target metrics. Just like this chart shows, it use less epochs. Okay, and the second important feature I want to talk about is the GPU transforms. Actually, I already see some questions and discussions about the GPU transforms in the chat. From MONAI 0.7, we added the PyTorch tensor support to most of the transforms. Now the transforms can support both NumPy array and the PyTorch tensor data. If the tensor is on GPU device, the transform will execute on GPU directly. So we can first convert the input data into GPU tensor by ensure type transform. Then the following transforms will execute on GPU. Usually, the GPU computation can be much faster than CPU computation, especially for the 3D imaging operation. Another acceleration is a cache logic. I think Michael already introduced how to cache the deterministic I/O and the transform. But even with cache dataset, we usually need to copy the data from CPU to GPU memory in every epoch. As the new released GPU devices already have a very big memory size, actually we can cache the deterministic data into GPU memory. Then we can execute the random transforms and the model computation on GPU to avoid the CPU to GPU copy. At the right side, I prepared an example code to combine all these GPU transform features. Here you can see that we load the image, add the channel dimension, change the image spacing, rotation, intensity range, and do some other transforms. With this ensure type, and the data type is the tensor. With this ensure type transform, we change the data into PyTorch tensor, and the two device transform moves the data into a GPU device. Here the cache dataset will cache the transform result until the first random transform. Here the first random transform is the random group by post neg label. So we cache the transform result of two device transform. So the cache data is on GPU. Then in every epoch, we get the cache data and execute the random transform on GPU directly. It can be very fast, and the GPU is not idle anymore. Another component we can optimize is the PyTorch data loader. As you know, PyTorch data loader uses the multi-processing logic to accelerate its data loading logic. But if we already cached all the data to memory or GPU memory, and the random transforms are light-weighted, just like this example. Actually, the random transform is light-weighted. So multi-threads may be even faster than multi-processing, because multi-thread can avoid the IPC time. And on the other hand, if we run transforms on GPU, the CUDA operations can't support multi-processing. So we developed the thread data loader to accelerate the data loading part. As you can see in the right chart, a separate thread is used to fetch data and execute the transform. The thread data loader will not pause after every epoch. There are two threads here. The first thread to process the data, and the other thread will load data to network. Okay. Before moving forward, let's stop for a while to see how to combine together all the skills we just talked about. I think we talked about AMP, GPU transform, GPU cache, and the thread data loader. So here we use the split segmentation task as an example. When testing on V100 GPU, we first applied the cache dataset and AMP. So the training time to achieve 0.95 mean dice is 153 seconds. And then we replaced the PyTorch data loader with the thread data loader. The training time decreased to 121 seconds. And then we also changed the transform chain to cache on GPU directly and execute the GPU transforms. The training time obviously decreased to around 50 seconds. So now we can train the split segmentation task within 1 minute from scratch to 0.95 mean dice on a single V100 GPU. If testing with A100 GPU, it can be even faster. I tested it once, it's about 40 seconds. And in this fast training tutorial, actually we also combined some algorithm optimization and GPU acceleration skills together. If comparing to a regular PyTorch program, here we used the dice CE loss function instead of the common dice loss function. Use the Novogratz optimizer instead of the common Adam optimizer. We also use the AMP cache dataset, thread data loader, and the GPU transform as we just talked about. So, sorry, as the left chart shows, with all these skills, we can achieve 0.95 mean dice in around 56 seconds. And the regular PyTorch program takes more than 11,000 seconds. It is more than 200 times faster. Okay, let's take a look at the real program, I think. This is the faster training tutorial. Here, if you run, this is the comment. If you run the faster training here, it will move the data to cache on GPU, same as the validation. And during the training, if we use the faster training, we will use the cache dataset. And if we use the regular training, use the common PyTorch dataset. And we also use the red data loader here to accelerate the training. And we also use the different loss function. This is the common training, and this is the faster training. And the different optimizer and the AMP logic. So let's run this example. Okay, first let's run the regular PyTorch training. Here I just run 20 epochs, but actually with the common Adam optimizer and the dice loss function, we need at least 200 epochs to get 0.95 in the regular PyTorch training. So you can see the training actually is very slow. We just train one epoch, I think. Okay, let's stop and go back to run the faster training. Sorry. Now let's execute the second cell. This is the faster training. First of all, we also cache the data as Michael did. Execute the cache data set here. Sorry. Here we cache. We set the cache rate to 1, so we will cache all the data. Yeah. A little bit while to cache the data. Now the training started. You can see it's much faster. It only takes 1.7 seconds for every epoch. See, here we do validation for every 5 epoch, and the first validation index is 0.5, and the second time 0.5. Yeah, as the 15 epochs, we already get 0.9. Now the training completed, we got 0.995, and the training time is within 1 minute. Okay, let's go back to the slide. After showing the spline example, let's move forward to a more excited topic: how to leverage a multi-GPU and a multi-node to continuously accelerate the training. Currently, the most popular distributed training methods are PyTorch DDP module and the Harvard framework. All the MONAI components can work well with them, and we prepared rich examples for reference. You can get all the examples here. Usually, we only need several simple steps to set up distributed training. First, we need to initialize the process group with the NVIDIA Nic Ma backend. Then set distributed model and distributed data sampler. And we only need to run some components on rank 0, like printing log and saving the model to file. And here is some test results of distributed training with the brain tumor segmentation task. With more GPU devices, we can achieve obviously faster training speed. As you can see in this chart, we tested with 1 GPU, 4 GPU, 8 GPU, 16, and 32 GPUs. Okay. And when we simply change the single GPU training to 8 GPUs training, the training time decreased from 25,000 seconds to 3,000 seconds. And the GPU utilization is around 70%. I think that because the brain tumor dataset is around 100 GB, and we can't catch all the data in memory or in the single GPU memory. But now we have 8 GPUs, so I think maybe we can optimize further. So we partition the dataset into 8 parts. Every GPU only need to catch 1 part. Then, same as the spline example, we execute GPU transforms and use the thread data loader. Now, every GPU need to catch about 15 GB dataset, and we run the transforms on GPU directly. As you can see in the right training curve, now the GPU utilization is always 100% during training, and the training time also decreased to 2,000 seconds. See, it's more than 10 times faster than the previous single GPU training. And we also tested with 32 GPUs in 4 distributed nodes. The training time is 800 seconds. And the GPU utilization is almost always 97% during the training in all the 32 GPUs. So let's try to run some real-time demo for this part. Okay. Something wrong here? Oh, sorry. My remote connection is connected.
Yeah, if you need a second to restart your connection and get everything started, then definitely feel free if you can.
Okay. Sorry, guys. Maybe, yeah, I need to Start the connection. Wait a minute. Sorry, guys. I used some remote server. Okay. Now let's see. I think we have 8 GPUs. All the 8 V100 GPUs are idle. Now let's try to run some program. Yeah, the test program is here. Just as I introduced, we partition the dataset into 8 parts. Every GPU only run on one part. Then we execute all the program here. We use the thread data loader, cache to GPU. Yeah, other things. Okay. Let's try to run. Okay, let's try to run on one node with 8 GPUs. Sorry. Yeah. Now we start to cache. You can see at the right terminal, the memory usage is increasing on every GPU. We are trying to cache the data on GPU. All the 8 GPU will cache the total data. Here we use about 13 GB to cache data on every GPU. I think. Oh, sorry, 15 GB. Now the training started. The training also need 10 GB to run the network. So the memory usage is 25 GB on every GPU. Now the training started. You can see the GPU utilization is always very high. The average value is around 100% during training. And we will not have the utilization drop after this epoch. Let's see. Yeah, now the training of this epoch stop. We don't have the GPU utilization drop because we are using the thread data loader. Okay. I think that's all from my side.
Okay, great. We do have some questions here in chat, so I'll try to go through and see if I can get all of them here. So one of the first questions was, are there any advantages to using create multi-GPU supervised trainer? The person mentioned that they noticed it can't take any handlers, and so they were wondering if you just used a normal trainer engine, and then you would build your distributed code around that. I guess what are sort of the benefits of using that multi-GPU trainer?
Oh, you mean the multi-GPU trainer in the engine?
Yeah.
Yeah. Okay. Actually, I think that's a very simple utility function in the engine part. If you really want to train a multi-GPU program with the engine, I would suggest to use the supervised trainer, and every process can run the trainer in parallel.
Yeah. Okay.
Yeah.
Great.
Actually, at the beginning, we don't support distributed training for the supervised trainer, so we have the the multi GPU trainer. But now all the supervised trainer and supervised evaluator can support the distributed training. Yeah.
Okay. Great. So the next question was, they asked, why was Novograd optimizer listed as a reason for achieving higher speed? And they're just kind of wondering, is it due to the choice of the optimizer, or why would the optimizer affect GPU acceleration?
Oh, actually, I think Dong will share some algorithm side optimization tomorrow.
Yeah.
So, yeah, that's some topic on his side. But
Okay.
I can show some brief introduction. We tried to analyze the data set, and the training curve is very smooth. So it is very suitable to use the Novograd optimizer.
Yeah. Yeah. And so
yeah.
I was gonna say, but Nick, what you mentioned is that so tomorrow we have a session by Dong, who's going to go over some more best practices for researchers, and I think he's going to dive a little bit more into optimizer choices and how that will affect performance overall. So I would definitely save some of those questions and bring them back up tomorrow during that session, which I think is our third session during tomorrow.
Yeah. I think Dong will have a very good presentation.
Yeah, definitely. Okay, I think I have a few more here. So one person asked, you have a telemetry slide or one of the slides you're doing telemetry on, they were asking what tool was used to visualize the telemetry performance.
Oh, you mean this slide, right?
I think so, yeah.
Yeah. Actually, this is the NVIDIA. Let me show you guys. NVIDIA NGC server. I think we have public access to that, right? NVIDIA NGC server. Maybe you guys can take a look at this one. And you see, yeah. For example, here is my jobs. I can submit a job to this server. For example, let me open the job and just show you guys.
Yeah.
Which one? Oh, this one. Yeah, you see, you can easily get all kinds of telemetry here. See.
Okay.
GPU memory and yeah.
Yeah, so this is just built into sort of the base command or NGC batch. I don't know, do you happen to know if there's any particular library that's being used or anything you're kind of reporting out to do the telemetry, or is it just kind of integrated into the platform?
I just use this NGC platform.
Got it. Okay.
Yeah.
No problem.
I think we have a public access to this one. Maybe guys, you can try to access NGC. Yeah, it's very useful NVIDIA server.
Yeah. Okay, I think we still have a few more. So someone asked, how many data sets have you tried your example on as far as sort of the performance and increase that you've gotten? And then with the cache data set, let's see, they asked, have you cached one batch or all of the training set as well during those examples? So I guess what data sets have you tried it on? And then, yeah, have you cached one batch or all the training set?
You mean the brain tumor example or the spleen example?
Yeah, I think they're trying to see, I think, how applicable it is to other, or how many data sets you've tested on to see if the performance increase. I would imagine that they're trying to see whether it's applicable to a lot of other data sets. So just wondering how many data sets you've tried it on.
Okay. Actually, we tried almost all the data sets in the decathlon challenge. There are 10 data sets in that challenge. The spleen, brain tumor. Yeah.
Okay.
And we also tried the pathology detection task. I mean the 2D classification task. We also tried that one, but we don't cache all the data. It's a very big data set.
Yeah.
Anyway, I think this is a common approach to cache data on GPU or on CPU memory. You can try it.
Yeah. Okay. And then someone did also ask for the caching data to GPU. memory? Does it happen once at the very beginning of training or for each epoch? How does it normally work for the caching data getting moved to the GPU?
Sorry, I didn't hear clearly.
Oh, yeah. So for caching data and it getting moved to GPU memory, does that only happen once at the beginning of training? Does it happen for each epoch or epoch? When does that normally happen?
Only once at the training, at the beginning of the training.
Okay.
Yeah, as you can see in the example, sorry, in this example, we here, we defined the transform chain, right?
Yeah.
The last deterministic transform is the 2 device. And as you introduced, we cache until the first random transform, right? So we cache until this transform. So the result of this transform is on GPU, right? So we cache until here.
Yeah, and that makes sense. And then that's because if you were to use something like smart caching or persistent caching, that of course would move things over in and out of memory more often. But it just is depending on what kind of caching mechanism. If you use a different caching mechanism, it'll differ when it's being transferred to GPU memory. Great. Someone asked for the parallel fast computing. Let's see, does MONAI version 6 also support parallel fast computing? So I think they wanted to know when sort of this got implemented and what version of MONAI were these things added. Are they available today in 0.6 or 0.7 or where are they, when was it released?
Oh, we already fully support the distributed training in 0.6. And in 0.7, we mainly optimize the GPU transforms part.
Okay, great.
I mean, I mean, in 0.6, we already fully support the distributed training.
Yeah,
you can find a rich example.
Yeah, I think that was everything. Someone did link to, so the notebook you're going over right now is the fast training tutorial notebook. That got linked in Discord as well. So if you want to go take a look at that notebook, run through it, look a little bit more at the code that Nick went over today, I definitely encourage you to go through and look at them. They are on there in our tutorials repo under the acceleration. And then here he's pointed out in the distributed training folder there. Yeah. In this folder, as I'm sharing, you can find the whole world example, smart cache example, and the PyTorch DDP example, and even how to use the workflows with DDP, things like that. Yeah. Great. I think that was everything, Nick. So I think I'll see if there's any other ones that come up in chat later on, but I really encourage you to stick around for next or tomorrow's session with Dong, where he will kind of continue on what Nick showed today and kind of go into a little bit more of the questions that were already asked about things like optimizer choices or some other pieces of best practices that you can implement as you're starting to look at your network and optimizing what performance can look like and what you might be able to achieve with some of the things we have implemented in MONAI, and just kind of generally assessing why you might be using a certain optimizer or a certain caching mechanism. And we'll go into that tomorrow a little bit more, but that was great. Thanks for the presentation, Nick.
Thanks, Michael.